This is a lecture by Farouk Alemi, narrated by Ungad Buttar. There are several ways to verify conditional independence. These include 1. Reducing sample size, 2. Correlations, 3. Direct query from experts, and 4. Separation in causal maps. If data exists, conditional independence can be verified by selecting the population that has a condition and verifying that the product of marginal probabilities is equal to joint probability of the two events. For example, in the table to the left, 18 cases from a special unit prone to medication errors are presented. The question is whether the rate of medication errors is independent of length of the work shift. Using the data in the table, the probability of medication error is calculated as 33%. Probability of having a long shift is calculated as 28%. Probability of having both error and long shift is 11%, and this is not equal to the product of the probability of each event. Therefore, error and long shift are dependent on each other. Knowing the length of the shift tells us something about the probability of error in that shift. But consider the situation where we were examining these two events among cases where the provider was fatigued. Now the population of cases we are examining is reduced to the cases 1 through 8 and is shown in the central table. With this population, the situation is different, and medication error is independent from length of shift when the nurse is already fatigued. The procedures used in this example, namely calculating the joint probability and examining to see if it is approximately equal to the product of the marginal, is one way of verifying independence. Other ways of analyzing the same data is to calculate the conditional probabilities or to use the chi-square statistical test. These have been demonstrated already. One way for verifying independence is to examine their correlations. Two events that are correlated are dependent. For example, we can examine the relationship between age and blood pressure by calculating the correlation between these two variables. If the correlation between the two events, e.g., age and blood pressure, is high, then it suggests that knowing something about one event will tell us a lot about another. Knowing something about the age of the person will tell us a great deal about the blood pressure. Therefore, the two events are dependent. Correlations can be used to verify conditional independence. To examine independence of an event A and B in population where event C has occurred, we need 3 pairwise correlations between A and B, between A and C, and between C and B. Events A and B are conditionally independent of each other if the product of the correlation of each event and the condition is equal to the correlation between the two events. Using the data in this table, we calculate the following correlations. Age and blood pressure have a correlation of 0.91. Age and weight have a correlation of 0.82. Weight and blood pressure have a correlation of 0.95. Examination of the data shows that the vanishing partial correlation holds as 0.91, is roughly equal to 0.82 times 0.95. Therefore, we can conclude that given the patient's weight, the variables age and blood pressure are independent of each other because they have a partial correlation of 0. It is not always possible to gather data. Sometimes, independence must be verified subjectively by asking about the relationship among the variables from a knowledgeable expert. Unconditional independence can be verified by asking the expert to tell if knowledge of one event will tell us a lot about the likelihood of another. Conditional independence can be verified by repeating the same task, but now within specific populations. Gustafsson and others described a procedure for assessing independence by directly querying experts. The steps are: write each event on a 3x5 card. Ask experts to assume a population where condition has been met. Ask the expert to pair the cards if knowing the value of one event will make it considerably easier to estimate the value of the other. Repeat these steps for other populations. Ask experts to share their clustering. Have experts discuss any areas of disagreement. Use majority rule to choose the final clusters. Experts will have in mind different, sometimes wrong, notions of dependence, so the words conditional dependence should be avoided. Instead, we focus on whether one clue tells us a lot about the influence of another clue in specific populations. We find that experts are more likely to understand this line of questioning as opposed to directly asking them to verify conditional independence. One can assess dependencies through analyzing maps of causal relationships. In causal network, each node describes an event. The directed arcs between the nodes depict how one event causes another. Causal networks work for situations here there is no cyclical relationship among the variables. It is not possible to start from a node and follow the arcs and return to the same node. An expert is asked to draw a causal network of the events. If the expert can do so, then conditional dependence can be verified by the position of the nodes in the arcs. Several rules can be used to identify conditional dependencies in a causal network. These rules include the following. Any two nodes connected by an arrow are dependent. Cause and immediate consequence are dependent. Multiple causes of same effect are dependent, as knowing the effect of one of the causes will tell us more about the probability of other causes. If a cause leads to an intermediary event that subsequently affects a consequence, then the consequence is independent of the cause for a given level of the intermediary event. If one cause leads to multiple consequences, the consequences are conditionally independent of each other given the cause. In the above rules, two events are conditionally independent if removing the condition will actually remove the path between the independent events. Another way to say this is to observe that event C is between events A and B, and there is no way of following the arcs from A to B without passing through C. For example, an expert has provided the map shown for the relationships between age, weight, and blood pressure. In this figure, age and weight are shown to depend on each other. Age and blood pressure are shown to be conditionally independent of each other because there is no way of going from one of the other without passing through the weight node. Note that if there was an arc between age and blood pressure, i.e., if the expert believed that there was a direct relationship between these two variables, then the conditional independence would be violated. The take-home lesson is that the conditional independence helps model building and can be verified in numerous ways, including querying experts, analyzing data, and looking for causal graphs. Please use the course website to ask a question and rate this lecture. This lecture will continue